You know, some coding problems get that hard label for a very good reason. But what if I told you the most elegant solution was hiding inside an algorithm you probably already know? Today, we're going to break down the reverse pairs problem, and we're going to uncover a really clever trick that makes it all click. Let's dive right in.
So first things first, we've got to be crystal clear on what we're even looking for. The problem asks us to count something called a reverse pair. What on earth is that?
Okay, so the rule's actually pretty straightforward. A reverse pair is made of two numbers from our array. The first number has to show up before the second one. Simple enough. But here's the kicker, the condition that really matters. The first number has to be strictly greater than 2 times the second number. That's it. That's the whole game right there.
All right, let's make this real. Take a look at this array. 1, 3, 2, 3, 1. Based on that rule we just talked about, nums of I is greater than 2 times nums of j. How many pairs can you spot? Go on, take a second.
And the answer is 2. If you got that, nice job. Let's break down why. The first pair is this 3 right here, and this 1 way at the end. Is 3 greater than 2 times 1? Yep, that's 1. The other pair is the second 3 with that very same 1. Again, 3 is greater than 2, so that's our second one. 2 reverse pairs in total.
Now, what's the first thing that comes to mind when you think about how to solve this? Your first instinct and my first instinct is to just check everything, right? Well, as we're about to see, that first instinct is a bit of a trap.
Yeah, the brute force method is exactly what it sounds like. You grab the first number, then you loop through every single number that comes after it, checking our rule. If it's a match, you tick a counter up by 1. Then you move to the second number and do it all over again. It's simple, it's easy to code, but is it fast enough?
And this table, wow. This really shows you the problem, doesn't it? For an array with 10 numbers, you're doing 100 checks. No big deal. But this problem lets the array size go up to 50,000. And at that scale, the number of operations just explodes into 2.5 billion. That's a lot.
And here it is, the punchline. There's just no way an algorithm this slow is going to get a big, fat, time limit exceeded error on any coding platform. So that easy, intuitive solution, it's a non-starter. We need something way, way smarter.
And that smarter way, well, it brings us to one of the most powerful ideas in all of computer science, divide and conquer. The strategy here is, it's beautiful, really. Instead of trying to wrestle this giant, complicated problem to the ground all at once, you just break it. You split it into these tiny, bite-sized pieces that are easy to solve. Then, you cleverly combine the answers from those small pieces to get the answer for the whole thing.
So how do we actually do that here? Well, this is the really clever part. We're going to hijack a super famous sorting algorithm that you've definitely heard of, merge sort, and we're going to add a brilliant little twist to it.
Just look at this side by side. A normal merge sort splits, sorts, and merges. Our version does all of that too. But the secret sauce, the whole trick, is that we sneak our counting logic right into that final merge step. That's where all the magic happens. Okay, let's zoom in on this merge step, because this is where it all clicks. Imagine we've already done the recursive splitting and sorting. Now we're left with 2 small sorted halves. On the left, we have 9 and 10, and on the right, 1 and 2. It's time to merge them, and, more importantly, to count. And this right here is the absolute game changer. Think about what this means. Because the left half is already sorted, if you find a number on the left that works with a number on the right, you instantly know that every single number after it on the left is even bigger, so they'll all work too. This lets us count in huge chunks instead of 1 by 1.
So let's actually do it. We grab the 9 from the left and the 1 from the right. Is 9 bigger than 2 times 1? Absolutely. And because the left is sorted, we know 10 is even bigger, so it also works with 1. Boom, that's 2 pairs right there, instantly. Okay, now let's check the 9 against the 2. Is 9 bigger than 2 times 2? You bet, which means the 10 works too. That's another 2 pairs. And just like that, we found 4 pairs. See how much faster that is?
So yeah, that merge sort trick is just chef's kiss. It's so elegant. But, and this is for all of you who like to go the extra mile, it's not the only way to solve this. The world of algorithms has other powerful tools in its toolbox. You might hear about these other advanced data structures, like binary index trees or segment trees. They can also crush this problem. They're definitely more complex to wrap your head around, but they're incredibly powerful for a whole family of problems that involve counting things in a certain range. Definitely something to look into if this stuff excites you.
And that's what I really want to leave you with. We took a standard, everyday algorithm, merge sort,
and we embedded a totally different job inside of it. We made it count pairs while it was sorting. So the question is, where else can you do that? What other familiar algorithms are just sitting there, waiting for you to sneak in some extra logic to solve a completely different problem? It's a really cool way to